So, this brings us to an end of the FDTD method, right. So, we will just sort of summarize the various aspects that we looked at, right. So, what did we start with? So, the flow of, because there were many modules over here, we started with, what was the first thing that we did? We took Maxwell's equations and did finite differences, right. So, finite what is the key concept for finite differences that we used to get accurate representations of the partial derivatives? Taylor's theorem. Taylor's theorem allowed us to see how to get the lowest error, right. So, once we had the finite differences, what could we do? What did we do rather? We discretized it, right. So, we made a stencil, right. The stencil was the E cell, right, and from here we got the so called update equations, which allowed us to step the fields in space and time. After that, what did we do? So, we had our update equations, we knew how to step it in space and time. We looked at stability, and before stability, well, yeah, so we looked at, we did analysis, convergence we did, and stability. This is where we got our Courant parameter, right, and we had that Lax-Richmare theorem as well. After that, what did we look at? We assumed a Courant stability factor is being satisfied, still we found that solutions were not always accurate. What was that? Dispersion, right. So, we looked at analysis, we looked at accuracy, and in accuracy we looked at, for example, dispersion, numerical. Okay. After having done that, so far we were still dealing with free space. Then we introduced materials, right. So, we looked at materials, we looked at simple materials which used Ohm's law, right. And after that, no, not boundary conditions, what we looked at another kind of material, no, one big, we spent a lot of time on this, frequency dependent dispersive materials, and which kind of model? Debye model, right. So, we looked at dispersive media, and in that we took the Debye model, right. So, we are able to, and this was important because in FDTD we want time update, and we got, here we got the correct relation between D and E, right. So, the relation D is equal to epsilon E is theoretically correct only when these are in the frequency domain, not in the time domain, right. So, we saw that exactly. Then after that we looked at materials are done, then we looked at absorbing boundary conditions, simple first order absorbing boundary conditions, right. So, absorbing then we looked at the inaccuracy of absorbing boundary conditions. For example, evanescent waves are not absorbed by a ABC. So, then the remedy was perfectly matched layers, right. So, we looked at PMLs, we looked at the theory via stretched coordinates, right. And then we looked at the implementation in FDTD. We were saying that absorbing boundary condition, the first order ABC, even if I implement it in a lossy medium where there are evanescent waves, even in a 1D case, the ABC does not give 0 reflection, it gives some reflection. So, it was a disadvantage of ABC. Okay. After having looked at PMLs, the last aspect that we looked at was sources, right. So, did I leave out anything? No. Okay. So, the last thing that I want to show you is this software which I have mentioned to you previously. Okay. I will show you. So, they have I mean I will show you the reason is, I mean, like MEEP, there are many softwares. The one big advantage of it is it is a software made by a academic group at MIT. So, it is open source and you know you do not have to pay money for it, it is free, right. So, it is one reason to promote it. We will look at one of their worked out examples to show you FDTD in action. Okay. So, we will just work through this.